last video, we have discussed an example, I guess example 5.7. Let me check. Okay. In the last video, we have discussed this example. Today, we are going to start a new topic, and this is the potential energy of a spring. So here we have a spring mass system. This is spring. This is block. Let's say it has mass n. And we are going to discuss the potential energy, kinetic energy, and total energy of this system. So one more thing here. Let's say the friction between this block and this horizontal surface is negligible or zero, you can say. This surface is frictionless. We are just considering it for simplicity, although there is no absolute frictionless surface. So let's say this is frictionless surface. Okay. Starting with initial situation, when this spring is relaxed, means neither elongated nor compressed, means there is no spring force acting on this block. Then let's say that situation is x equals to 0, means the position we are taking x equals to 0. And now what will happen if we move this block from here to a new position? Let's say this position is x along positive x direction. Then the spring will get elongated and it will try to pull this block back to equilibrium. Okay. What if we have displaced this block other way here? In this case also, the spring will be acting on this block. Let's say this is minus x. But this time the spring will act along positive x direction. So one thing here we can see that the direction of this spring force is opposite to the direction of this displacement. And one more thing, this spring force is directly proportional, means it varies linearly with this displacement. So if we want this, we can check experimentally. If we want to remove this proportionality sign, we have to add some constant here, that is constant of proportionality, and into x. And we are discussing the things in one dimensional scenario here. So the direction can be taken into account by just using positive or negative sign. So here we are going to add a negative sign. Why this negative sign? Because in this scenario it is showing this spring force is opposite in direction with this displacement. Okay. So this proportionality constant K is called spring constant. And it may also show that how stiff a spring is. Let me take it to other slide. Let's say you have two different springs, one with spring constant K1 and another with spring constant K2. Same mass attached. Okay. And if you displace this mass x here and this also by the same amount, and you experience that spring force in first case is more compared to the spring force in second case, then you will obviously get here Fs equals to minus kx. Let's drop this minus sign because this is for direction, not for magnitude. So Fs in magnitude will be kx. And then if for the same displacement, Fs is more, it means this k is more or k is greater. So here in this case, K1 is greater than K2. Other way, you can say if spring constant is greater, the spring is going to exert more spring force, or you can say the spring will be stiffer. Now, from here, you can say this K equals to F by X just to get its SI unit. So its SI unit is Newton and displacement has SI unit of meter. So Newton per meter. Okay. Now we are going to plot this Fs equals to minus Kx. We are going to plot this thing, spring force versus displacement graph. So this is a very easy graph. You can see first Fs equals to minus Kx. This is linear graph in X. So if this is x-axis and this is, let's say, Fs, you will get a graph like this. And excuse my drawing. This is a graph of Fs equals to minus Kx, where K is the slope, that is K is the tan of this theta. So this is a separate thing to discuss about graphs, but here this particular graph we are going to discuss. So this will be Fs equals to minus Kx. Okay, let me take a already plotted graph so that it will be more clear. Here, Fs equals to minus Kx. And let's take a point on this graph. Let's say this is point A, where the displacement of, although not necessarily, but in this particular case, let's take the displacement is maximum, which we have denoted here with xm. So with this displacement, let's say here the force is minus k times x into m. And then this shaded area will be, you know, if you have, this is a geometrical representation. If you have force on one axis and displacement in other axis, so the area under this graph gives you force times displacement, which is work done. In this particular case, the same thing is happening. So this area will give you, this area is 1 by 2 into base into this perpendicular. So ultimately it is going to come minus kxm square by 2. So this is the work done by the spring force when the block is displaced from x equals to 0 to x equals to xn. Okay, you can take any general x, not the maximum one only. You can take any general. Let's say we have displaced, let's move to the analytical discussion for the same. That was graphical representation. Now we are going to do it analytically. So let's say here x equals to 0 and here x equals to maximum. And if you have moved from here to here, we have already seen all this scenario, but let's take some intermediate point x here. Okay. So if you have moved from here to here, this block, the spring force will be at this particular point will be minus k, the spring constant is k, and this is m. Although we are not going to use right now, but we are going to use further when we start discussing about kinetic energy. So this k times x, and one thing is here, if we want to get work done by this spring when this block is being moved from x0 to xm. The work done is, let's say, work done is something force into displacement. Okay, if force is constant, then the situation is very easy. If force is constant, we can just multiply force with displacement, or if there are vectors included, so we can do just force times dot product, force dot displacement, and this will be work done. But what is here happening? The force is not a constant quantity, rather it is varying with displacement. So we have to make another approach here, and we are going to do it by integration process. How? Let's take the force Fs equals to minus kx at this position, and we have displaced a very little. I'm showing this much span just to make it visible. Let's say small displacement dx. So from here to here, if we have chosen a very small displacement, in this short interval, we can take this spring force to be constant. This is what the process we are going to obtain work done. So, and this is what we have chosen a very small displacement so that we can take the spring force to be constant. And now, from here to here, in this span, we can take small work done dw and fs into dx. Very simple. But when we are going to obtain work done from x equals to 0 to x equals to xn, we have to take all such small intervals. Let's say we have divided this span, this displacement into a small intervals of dx. So we have to take all small dw's and we have to add. And here we are going to take integration approach because this is the way we are going to obtain. So work done will be x equals to 0 to x equals to m, and then this fx dx. We are integrating in this range from x equals to 0 to x equals to xm. And as we know, 0 to xm, this is minus kx, force equals to spring force, and this is ds. Now, minus k is constant, we can take it out from this integration sign, and x 0 to xm, and we will have x dx. And if you have gone through basics of integration, you can easily solve it. This will be x square by 2 from 0 to xm, and then the work done will be minus kx m square by 2. Okay, here you can try by yourself from here to here, although I have done at least one step. Okay, so this is work done. And now, as we can see here, this work done is depending on position. So let's say, let's say this spring force is acting on this block, okay, and some external force has moved this block from its equilibrium to x. maximum and then brought it back to this position. Okay, now let's say some external force Fa, but we are not uh, going to be considerate more about this because we are dealing with this spring force here. Okay, so there must be some force to displace, some external agency to displace this block, but we are more interested in this spring force. So for time being, we are not going to calculate these things. Okay, later on we can discuss. But here, what is happening? Work done from here and then from here to here. What will be the total work done? So we can check it. Work done is 1 by 2 k x square and minus n here. So if you want to check from here to here, this will be minus 1 by 2 k x m square. Okay. And from here to here means from xm to x0. In this particular scenario, look what is happening. In this particular scenario, this displacement is going to be from xm to x0. Okay. So if we are going to get this work done, let's say fs dx, and in the first case it is 0 to xm, and in the second case it is xm to 0. You can see it easily. It is going to be 0. Okay, I'm leaving this part to you. Just solve these two integrations and then you will arrive at this sim. So what is happening on a round trip, means starting from x equals to 0 and coming back to the same situation, the total work done is 0. And this happens in case of a conservative force. That is, spring force is a type of conservative force here. The work done uh, is going to be 0 in a round trip. Okay. Now we are moving to potential energy. So what will happen? If there is some work done by a conservative force, the negative of that work done is going to be the potential energy rise in the system. Okay, let me make it more clear to you. Suppose you have already seen this kind of problem. If you have lifted a ball from certain height to a next height here, the gravitational pull is going to work against this movement, and then the work done will be something negative here. But there is rise in potential energy, and that rise, let's say this is very a small displacement, so that this mg is not going to vary too much, means this gravitational acceleration due to gravity is not going to vary too much. Then there will be, look, from here to here, there will be rise of potential energy by an amount mgh. What is happening? The work done by this gravitational force is something negative, but that negative work done, which is done by this gravitational pull, it is being reflected in rise in potential energy of the system. The same argument we can carry forward here also. If there is spring and you have applied some external force, yeah, the work done by that external force will be positive, because this is what happening. External applied force is here and the displacement is also along this force. Then work done will be positive. What is this work done? This is done by this external force, but we are not uh, interested much in this. We are interested in the work done by this spring force. So what is happening here? A spring force is doing work done, and that is some negative kx square by 2, and by the same amount there will be rise in potential energy, because negative of this, that is kx square by 2, is the work done by the external factor, which is going to increase potential energy of this spring mass system. So in easy way, we can say the negative of work done by a conservative force is the amount by which the potential energy will rise in the system. Okay, so let's, and of course, there will be movement. If you release this mass from certain displaced condition, let's say this spring is elongated and you have released it, it will start moving and it will eventually reach here. And of course, it is not going to stay here if this is frictionless or no other things stopping this block here to stay, then this will overshoot this position. And now there is a question, what will be this velocity? Let's say this is Vm. So what is happening? From here to here, this block is being moved and the potential energy of this system is rising. After moving here, let's make the system free from any external force. Then this block will start moving this way. So at this position, the velocity of this block is 0, but when it starts its journey, it will experience some spring force, and that spring force will bring acceleration and its velocity will increase. And after reaching this equilibrium position, its velocity will start decreasing, because after this spring will start to be decompressed, and then the spring force is now opposite to the motion. So eventually there will be a point xn in other way where it is going to stop again it will be with zero velocity here. This is xn. So at this equilibrium position, its velocity will be maximum. Again, I'm mentioning this thing. When we are going to study simple harmonic motion, we are going to discuss this, these all things related to its motion in well detail. So for time being, let's say the maximum velocity Vm here. So what is happening? It has some potential energy here, minus of minus kx square, that is minus of work done by this spring force xm square divided by 2. And when it reaches to this point, its potential energy drops to 0 again, because x is 0 again here. And then the entire potential energy is going to give rise in its kinetic energy. Means it is moving here with the maximum velocity, what it could be possible in its entire journey. So we can say at this point, let's move to the next slide. At this point, the kinetic energy will be 1 by 2 mvm square, and this will be numerically equal to the 1 by 2 kx square, because this much energy this system had initially, and then it is giving rise to the kinetic energy. This was potential energy, maximum potential energy. So xm here. So what will be Vm? Vm will be Vm square will be k by m xm square, and Vm will be under root k by m xm. Okay. Again, here you will get two different things. One is plus, one is minus. If you are going to remove this square root, this square. So, okay. So one will be towards this way. And again, in the same motion, after after reaching this point, let me use some different color here. After reaching this point, this block will again start moving to the equilibrium, and it will overshoot this point once again, but this time velocity is along positive x direction. That's why we have two things here. One is positive and one is negative for two different maximum velocities at the equilibrium point. Okay. And if we want to draw a combined graph for kinetic energy as well as potential energy, kxn square by 2. Mind it, this is for maximum velocity and this is for maximum displacement. But there are intermediate situations possible. There are intermediate situations where x is not xm, but it is somewhere between 0 to xm. And in the same way, there are situations possible where velocity is not velocity maximum, but it is somewhere 0 to Vm. And you can easily figure out that at this point, its potential energy is maximum. This is 0. And at this point, potential energy is 0, kinetic energy is maximum, that is, velocity is maximum. Okay, and the same argument we can carry forward to other side. Here, velocity is 0, again kinetic energy is 0, and potential energy is maximum. So we can plot these two, kinetic energy and potential energy, in a single graph, and then we can do a comparative study. Just few minutes more. Here is the thing. This is showing potential energy. Look, this is a parabola, as potential energy is something proportional to x square, and this is kinetic energy. Okay. So the potential energy and kinetic energy, these two are shown on a single plot here, and you can see they are both varying in a parabolic form, and where the potential energy is maximum, kinetic energy goes to 0, and where the kinetic energy is maximum, potential energy goes to 0. And the same argument is coming to this side also. Here, at this point, potential energy is maximum and kinetic energy is again 0. Okay, let me clean it. So this is what this plot is showing. And finally, you can see here, there is a straight line here. This is total energy which remains conserved during the entire motion. Means the sum of this kinetic energy, it is written here, the sum of this kinetic energy and potential energy, this will be always a constant quantity, unless there is a non-conservative force. We have discussed about conservative and non-conservative forces. So if there is no energy dissipating force here, pure conservative forces acting here. Only conservative force is this frictional force. Sorry, this spring force. There is no friction or something dissipative force. So the total mechanical energy remains conserved. This is what shown with a straight line without any slope parallel to this position axis. So this is all for this class. Next time we are going to take a few examples to consolidate our concept of this kinetic energy and potential energy, and of course spring mass system. And okay, that's all for this video.